Today I'm going to talk about this topic, directed evolution of Cas9 to increase its specificity. So, whenever people use CRISPR, one of the major concerns is how specific is it. So, lots of people are interested in increasing the specificity, and there are already many methods to increase the specificity. For example, you can modify sgRNA. You can add additional guanine at 5' end of sgRNA. This is because every sgRNA needs to be expressed in cell, and mostly people use U6 promoter, and in that case, every RNA transcribed from U6 promoter start with G, and people realize that addition of G increases the specificity of Cas9. Also, people truncated sgRNA, the spatial sequence from 20 to 17 mer. So shorter the sgRNA, the higher the specificity. And also, people modified Cas9 protein. One group, instead of using one Cas9, they used two Cas9, but instead of introducing double-strand break, it introduced paired nickase. In that case, because there are now two Cas9 protein that is required, it shows higher specificity. And also, people use site-directed mutation of Cas9 protein based on rational design. So it appears that all these strategies, the aim is avoid off-target while maintaining high on-target activity. So today I'm going to talk about two topics. First one is called Sniper Screen. This is the screening method that we developed to increase the specificity of Cas9 using directed evolution approach. The second is Sniper Cas9, which is the mutant Cas9 we obtain from such screening. So there are two approaches people take when modifying enzyme properties. First one is called rational design, and second is called directed evolution. And first one, you really need a rational design. You really need a good crystal structure, because once you have crystal structure, you can have good guess about how it works, and you do experiment called site-directed mutation of the point of interest, and then you can test the mutant enzyme, and then go back and forth until you reach satisfying property. The second is called directed evolution. For this one, you really need a good screening system. Once you have a good screening system, you can introduce random errors to the enzyme, and then you can also shuffle, which is quite similar to homologous recombination that occurs in nature. So this flow of experiment can be repeated until you reach a hit that satisfies you. So there are already three enzymes that appeared in literature based on rational design approach. So everything started when Professor Nurecki discovered Cas9 crystal structure in 2014, because the two groups, one in Gongsan and the other is Kiss-Jung, and Harvard group made rational guess about how it works, and then made site-directed mutation. For example, Professor Gongsan group made mutation here, and Professor Kiss-Jung made mutations there, and then successfully increased the specificity of the Cas9 enzyme. And more recently, this year, Professor Daodana group did further mechanistic study, and instead of these two regions, they mutated RAC3 domain based on their experiment, and also modified the few residues here, listed here, and show that it shows high specificity. And one thing I really like about this Professor Daodana paper is that they did a side-by-side comparison of these three enzymes. So you can see that this is off-target result, and you can see that compared to wild-type SPCas9, Indeed, this HF, ESP, and cluster 1, which is from Professor Davena's group, shows higher specificity. And it appears that these are quite similar in terms of specificity. It appears that cluster 1 and HF1 is slightly better than ESP, but this comes, this sacrifices the on-target activity because this is on-target activity compared to wild-type Cas9. So this dotted line here is 70% of wild-type Cas9 activity. You can see that although there are lots of targets above 70%, for some targets, the on-target activity actually decreased. And it appears that instead that ESP Cas9, although its off-target specificity is slightly lower than the other two, it shows higher activity, and also these other two, although they show higher specificity, their on-target activity is kind of injured there. So, and also one thing I really like about this paper is this conclusion remark. So this is, if we can do the thought experiment. So suppose there are two Cas9 enzymes in nature, one with very high specificity and one with mediocre specificity. You know that bacteria use Cas9 as an immune system. Which one do you think has the higher chance of survival? The answer is that the one with mediocre specificity has higher chance of survival because, as you know, viruses and foreign invaders make frequent spontaneous mutations. And if the Cas9 is very, very specific, it no longer acts on those invaders. So in nature, the one with a mediocre specificity actually have higher chance of survival. And as a result, we can have fairly good guess that all the Cas9s found in nature may have not good high specificity. This leads us to think that maybe we can make a selection scheme, directed evolution, particularly directed evolution, which can be used to select for the higher specificity of Cas9. That's what we made, and we named it Sniper Screen. So I'll walk you through how we made it, and then I'll explain the logic behind it later. So first, we PCR EMX1 gene and embedded into the genomic DNA of E. coli using transposase system. And then we can transform such E. coli called BW25141 EMX1 with two sets of sgRNA. The first one expresses sgRNA. The second one expresses CCDV gene, and this sgRNA has mismatched to EMX1 sequence here, but is perfectly matched to the one in the CCDV gene. Such E. coli we named Sniper Screen because we can transform this with random library of SP-Cas9. And once induced by these two different sets of inducer, the surviving colonies actually contain the Cas9 mutant with higher specificity than wild type. This is because there are only 4 possible scenarios for this E. coli for survival. For example, if SP-Cas9 shows no activity, then this sgRNA will not cut this perfectly matched CCDV gene. In that case, because their CCDVs are no cut, then it leads to cell death. Wild-type Cas9, on the other hand, when the sgRNA is expressed, even if there is a mismatch in the genomic DNA, it can still cut the genomic DNA. And E. coli, if there is a double-strand break in genomic DNA, it doesn't have a repair system, so it dies. So it leads to cell death. So only if when the SP-Cas9 variant cuts this perfectly matched CCDV gene and doesn't cut the EMX1 genomic DNA with mismatch, then E. coli survives. That's the surviving colonies right here. also we can collect all the pools and then repeat this until we get the colonies that we want. So this system works in only one condition, that wild-type Cas9 cuts the genomic DNA. And that's why we embedded EMX1 gene into the genomic DNA of E. coli. Because Professor Feng Zhang, back in 2013, did this extensive screening. You can see that here are the mismatches to original EMX1 gene, and he screened all the different mutants, sgRNA, and this one showed highest activity compared to these 4 targets. And also within this, you can see that there are some mutations show high activity, some mutations doesn't. So we only select for the one showing the high activity, because if it shows high activity, it will cut the genomic DNA. If it doesn't, then it won't. So it works only if they show high activity. So we select for the ones with high activity, which is selected there. So, so this is actual screening we did. We first introduced random errors using method called error-prone PCR, and also from these 2 vendors. And also we use mutant string from Agilent. So these are 3 different types of library we constructed, and overall the diversity reached something like 10 to the 7. And then we did screening, and these are the mutant sgRNA we used for such screening. You can see that we started with that most lenient one, with only 5% in the, which is like 2 mismatches in the seed region. The second screening was more stringent, which is 2 mismatches in the non-seed region. And then you can see that this is the screening. And then we did something called shuffling. And then I did screening with 1 mismatch in seed region and 1 mismatch in non-seed region. And you can see that the percentage of survival goes up, and then after shuffling it goes down, and then it goes up. So the second screening, I ignored these 2 mismatched one, and also I didn't do shuffling, and then just did it as a control. And you can see that why the shuffling is very needed. The one with shuffling, this is the pooled library at the end, and I used it for the, I transfected into mammalian cell and checked the specificity of the pool. And you can see the one with the shuffling show higher specificity than the one without shuffling. So we selected this pooled library with shuffling. And then we sequenced hundreds of them, and then we only got 3 different mutant Cas9s, which we named Sniper1, Sniper2, and Sniper3. And these are the mutant points, and as you can see, because I did random errors for whole sequence, these are dispersed throughout sequence, and also to my relief, no position overlapped with previous ones from ESP, HF, and hypercasnet from the Ardena group. And Sniper1 is the one with the highest activity, and we did extensive site-directed mutation studies based on these. But it appears that screening system really works well, because these studies show that original Sniper1 is the best one. So that's where we come to collaborate with Dr. Jin-Soo Kim, because we want to compare this with famous ESP and HF, and his lab was willing to help us to do that. And here are the targets we use in mammalian cell test, and you can see that it's in 2 different groups. The first one is the one used by these Harvard groups. This has characteristic that it all starts with G. This is because, sgRNA start with G because of the U6 promoter, and they only chose targets starting with G so that they can have perfectly matched sgRNA and target like this. But sometimes if we increase the length to 19 to 20, then you will show mismatch, which we designate as small GX20. And this perfectly matched one we designate as large GX19. Some other targets, they don't start with G, so we designate them each small GX19 and small GX20. And you can see the result here. This is the result on-target activity compared to wild type. And you can see that this ESP and Cas9HF, none of them showed higher activity than 70% here, and only one showed here. Whereas Sniper showed, all of them showed more than 70% of Cas9. This is because we use screening in this small GX20 format, so that Sniper 1 was selected to perform well in this condition. And also for this small GX19, only one passed above 70% for ESP and one passed for HF4. And Sniper 1 again showed more than 70% activity in all the targets. And for large GX19, indeed ESP, all of them showed more than 70% activity. So this confirms us that experiments were done in correct condition, and that because Professor Fang Dang did all his experiment in this condition, they actually performed well in this condition. HF4 on the other hand, only one passed, and this week I met Professor Kis Jung, and then he told me that I should have used HF1 instead of HF4. But we did this because HF4 with the highest specificity, whereas HF1 was one with the highest activity. So we really wanted actually to compare this point, because this point was more than 70% activity. Now, with this FANCF01 gene, we can compare all the three and wild type for the specificity. And you can see that here, this is wild type large GX19. This one is on target and this one is off target. And the ratio between off, above, on is this off-on specificity ratio. And you can see that compared to wild type, ESP and HF4 indeed show higher specificity, which can be shown by this decrease in the ratio. It appears that Sniper in this large GX19 condition shows worse specificity compared to the other two. But again, I have to tell you that we did the screening in this small GX20 condition. So, and also we have to just ignore these 2 points because on target was too low that it's not fair to say the specificity ratio was 0 for these two. So let's ignore these two. And if we compare these two with Sniper in small GX20 condition, it appears that it performs slightly better. But the difference was too small that I wouldn't say this is actually better. And this is also a finalizing slide for specificity comparison. And you can see that one passed above 70%, so I calculated here, but for the targets which showed below 70% activity, I just didn't put it because they're quite misleading. And you can compare that for small GX19 condition, there's one gene that passed above 70% for ESP, and our one performed better here. And also for this one, these 3 points were quite similar to these 3 points, whereas there are 2 points that didn't show high specificity, actually 3 points. But these ones, our one performed a little better, and only one was above 70% of activity for HF4, which was the gene I compared before. And this is another screening that we did. This is wild type on target activity. And unfortunately for this target, ESP and HF didn't show high activity, so I wasn't able to compare the specificity. But compared to wild type, Sniper showed similar on target activity. And you can see that I made SNPs throughout the sgRNA, and it appears that for the middle ones, the ones with SNPs in the middle region, indeed sniper shows high specificity, whereas like the ones at the end, they don't show much specificity. And this one can be explained because, as I told you, we can truncate sgRNA to increase the specificity. So we can, instead of using GX20 form, which was used here, we can use GX19 form, then we'll remove these points. And also, there are two mismatches, and Sniper didn't show any off-target, whereas wild type shows some off-target. So here's a summary. Sniper screen is one novel one-step screening system for high specificity in E. coli, and also the Sniper Cas9, which we found, maintain wild-type on-target activity and improve specificity in many different targets. With that, I would like to thank the rest of the Toolgen members, and also Professor James Kim and Wei-Hwan Jung, who did all the comparison tests. Thank you very much.
Thank you, Dr. Lee. You have time.
저는 제주자는 처음인데요. 제가 영어로 발표하는지 모르고 왔습니다. 어쨌든 준비는 영어로 하긴 했는데 이렇게 큰 학회인지도 몰랐고요. This is first time to attend the genetics conference in Korea. Actually, I am the veterinarian. I'm working in an hospital in Seoul National University. Probably I saw several posters in coming here, and there are a lot of kind of the major coming here. So probably in here somebody didn't know what I am doing. Also somebody doing the what is the animal like that. So this is the kind of the review. So just really briefly thinking, don't considering the very deeply. So I'm just why I have to slide this one. Animal is very important thing for in life science. Most of the recently three Nobel Prize. First one is the mouse embryonic stem cell. Second one is the IVF baby, tube baby. Third one, induced pluripotent stem cell. It's almost a similar developmental biology breakthrough in life science. Also, another analysis in the Nobel Prize, many kind of study was derived from based on the animal study. But still, many species, also some of the plant area, they believe the plant is most important thing. But I believe it's also animal is very important thing. It's the different aspect. So why we have to make the animals? Because basically we know in life science area we have to know the function, particularly gene, like the target gene. What is the target gene like that? So to know the target gene understanding, we have to make some gain of function or loss of function. To do gain of function, currently a lot of kind of the over 10,000 kind of the gain of function mouse or several kind of pig, dog, another some species, including plant. Maybe I don't know how much it is in over the world. In Korea also many kind of the transgenic animals, including the plant, exist. Technology very fastly optimized, applied in many areas. So currently, many laboratory we can produce the kind of some transgenic animals like gain of function. This is the representative picture of the mouse or pig, zebrafish or chicken. So maybe somebody, this is first time to see like the GFP chicken. You can expose the LED signal and then GFP eliminate the green fluorescence. Also there are red fluorescence, the chicken exists. Another looks like the pig. The blue pig, red pig exists. So in China group recently, they didn't publish it yet, but they successfully generating the rainbow pig. Rainbow